Gonzalez-Bouchard, I have a few announcements to make. First, let me thank the Anthropology Department and the Maxim Museum for allowing us to use a hidden center for each of our 4 talks. This is the last in the 4. And I also wanted to acknowledge our gratitude to the Robert Wood Johnson Foundation and to the faculty and staff at the Center for Health Policy for sponsoring our lecture series and for all the administrative support. If you haven't done so already, please sign in so we can keep a record of your participation and let you know about upcoming events. There are some clipboards that might be going around as well. If you haven't already seen the flyer for the next 2 talks that are organized by the center, on April 9th, we'll have economist Professor Marie Mora, who I understand will be visiting here in the spring, and she will be speaking about self-employment, disability status, and race ethnicity. And on May 27th, we'll have Dr. Ellen Marie Whelan, who will speak about the winding road of healthcare. So the title of this lecture series is called Troubling Race, in quotation marks, Cutting Edge Research Design Across the Disciplines. Our objective with this series is to initiate a conversation about how to study race and inequality that transcends traditional disciplinary boundaries across the biological and social sciences. We believe that this conversation has to be transdisciplinary because the problem of conceptualizing and operationalizing race in research design is transdisciplinary. We hope that this series of public conversations will push scholars, community members, and students alike to think critically about how they conceptualize race and how they engage race in their research design and public policies. We believe that this is a necessary first step for scholars and policymakers who seek to advance social justice. So let me go over the logistics. Dr. Gonzalez-Bouchard will present for about 45 minutes. Then we'll have Dr. Bill Reese give us the first question. He's the Associate Director of the Robert Wood Johnson Center for Health Policy and also a medical doctor. We'll have Carolyn Montoya, who's a Robert Wood Johnson doctoral fellow, follow with the second question. And without further ado, let me introduce Dr. Gonzalez-Bouchard, who we are so delighted to have here at UNM. Dr. Gonzalez-Bouchard is an associate professor of biopharmaceutical sciences and medicine and director of the clinical pharmacology training program at the University of California, San Francisco. He earned his MD degree from Stanford University School of Medicine. He completed clinical training in internal medicine at Harvard's Brigham and Women's Hospital and pulmonary critical care medicine training at the University of California in San Francisco. He earned an MA in clinical effectiveness from Harvard. He earned an MPH degree in epidemiology from UC Berkeley. He earned a Bachelor of Science degree in cellular and molecular biology. He has earned many awards, including the Robert Wood Johnson Harold Amos Medical Faculty Development Scholar, and he is keynoted for the American Lung Association and the National Medical Association. Dr. Gonzalez-Bouchard has mentored numerous students. He teaches courses in genetics and the importance of race, ethnicity, and biomedical research and clinical practice at the School of Pharmacy. At the School of Medicine, he teaches courses on pulmonary physiology and pathophysiology. Dr. Gonzalez-Bouchard has been a prolific researcher, publishing in peer-reviewed journals such as Human Genetics, the American Journal of Respiratory Critical Care, Transplant Immunology, Pharmacogenic Genomics, as well as many other journals. He's also a champion wrestler, so beware.
70 pounds ago.
Many years ago.
70.
So join me in welcoming Dr. Gonzalez-Bouchard.
Thank you. Well, thank you. It's an honor and a privilege to be here. So I've been given a difficult challenge because I do genetic research or translational genetic research, and I know most folks here don't know genetics. So I'm going to begin with the primer in genetics. If there are any questions, please feel free to just wave your hand slightly and I'll pause. But we're going to go from some basic genetics 101 to some of the most advanced genetics going on in the field right today. So we're going through a pretty fast pace. But I'm going to talk about, is there a way that I can lower these lights? I'm going to talk. Okay. Whoops. It's too bright, too dark. All right. I'm going to talk about a project that I've been doing since 1997. And it's been my life's work, my academic work since that time, and it's actually grown and expanded. We've actually have expanded to several other populations, but the two populations I'll focus on are Hispanic populations. So just very simple. In my view, it's easy to use analogies and to have an infrastructure to hang new terminologies on. And the way I like to think about genetic variation, which is what I'll talk about, is using analogies from our English language. The English language consists of letters, and we interpret those letters to make words, and the genetic code consists of what we call base pairs, and we interpret those base pairs, a combination, to make genes, and the combination of several words makes a sentence, and the combination of several genes theoretically could make a haplotype, and paragraphs are organized, chapters are organized, and our genetic structure is organized just like chapters, and we call those chromosomes. 23 chromosomes, going from the largest being number 1 all the way down to the smallest. So how about genetic variation, and why is it important? Genetic variation, when I think about it, is if we were to look at analogy with a word, so in this case the word bear, B-E-A-R, if you photocopied that word and made it, you would go ahead and make a bear, B-E-A-R, and then it's the instructions, it's the blueprints, and tells you what your body should do. Go make a bear. But what if there's a misspelling and you had a single letter change from B-E-A-R to B-E-E-R? Just a single letter. It could be innocuous. It's a single base pair change or misspelling. But the end result is drastic. When you get the instructions on how to make something, instead of a bear, you're making a beer. A single letter change. Now that's exactly what happens in genetics. So when we talk about a gene, your cells are constantly dividing, and when they divide, they need to photocopy the blueprints on how to make cells or how to behave. And if they do it correctly, they'll go ahead and, in this example, make a copy of this gene, which is composed of letters or base pairs, ACTG. Duplicate would be ACTG, and it tells it to make a protein following that pattern. But when there's a base pair change or a misspelling, and there's infidelity or mistakes happening all the time, that instead of a ACTG, you get an ATCC, and it tells the body to go ahead and make a protein that corresponds to that. Well, a single base pair change is exactly what happens with common diseases like cystic fibrosis. Everyone has the cystic fibrosis gene, but there's a one base pair misspelling, and it leads to a dysfunctional protein. And that protein in the lungs doesn't transport water very well, and so kids that develop cystic fibrosis develop chronic lung infections because their mucus is too dry. The same is true for sickle cell anemia. There's a single base pair change, and it causes sickling of blood cells, and that tends to be more common in folks of African ancestry or Mediterranean ancestry, whereas cystic fibrosis is common in Northern Europeans. So there's some racially specific differences, but again, it's a single base pair change. So here's the big debate. And when I started off my career, I didn't know I'd be doing this, and I kind of fell into this fortuitously. But the big debate has been whether race or ethnicity should be considered in studies of disease or even drug response. And unfortunately, the media and academic societies, communities, have binned us into one of two camps. Race is either a social construct or a biologic construct. And people have been pretty abstract about that. And the media likes to paint us, to bin us into one camp or the other. And it's almost as though in the literature we throw stones at each other and don't talk to each other. And that's actually quite relevant because the demographics of the United States are changing. And what you can see is that, this is from 2008, that the diversity of America, the diversity of people that are contributing to the tax base, which funds publicly funded research, like research that I do, research that people do through the National Science Foundation, is increasingly coming from a diverse population. And therefore, we need to be more mindful of who we include in research. And so an obvious question is, Does race and ethnicity matter? Well, this is an old slide. For the geneticists, forgive me, but what this slide did was they took 4 racial groups: African Americans, Asians, Hispanics, and Caucasians, and they looked for genetic variation in about 300 genes. So they looked for those misspellings in 300 genes. And they simply cataloged the distribution of those misspellings across racial lines. And what they found was pretty cool, is that about 25% of the genetic variation out there was cosmopolitan, meaning that if we studied one group, Caucasians, we'd have identified the same variants in other populations. And that wasn't a surprise. That, the politically correct people like that because we can all hold hands and sing Kumbaya and say we're all the same. But what they also found was that about 12% of the genetic variation out there was private or racially specific, meaning that if we only studied Caucasians, we would have missed a lot of genetic variation that was relevant, say, in other populations, African populations, Asian populations, and so forth. And so now, this is kind of a paradigm shift back then in 2001, but now it's generally accepted that there is racial genetic variation. Some of it is 0-1, meaning all or none, but a lot of it is a gradation, going from, say, south to north. You might see a gradation in gene frequency or frequency of mutations, or genetic variation. Well, this is actually quite relevant because this is happening and now affecting everyday medicine. And I took this quote, I got it a couple of weeks ago. I went to Rite Aid, which is down the street, and I asked the pharmacist for the package insert for carbamazepine. Carbamazepine is a neuroleptic drug. It's a drug that we use to treat seizure disorders in children. And here's the package insert. And it specifically says, the important part I highlighted, patients with ancestry and genetically at-risk populations should be screened, blah, blah, blah. And what they're talking about, what they further went on to say, is that if you are Asian and you're considering taking this drug, you need to be genetically tested. And the reason is Asians have a genetic misspelling, a genetic variation that in conjunction with this drug leads to life-threatening skin disorder called Stevens-Johnson syndrome, in which all of your skin sloughs off, you get infections, and you die. So this is a good example of where geographic ancestry, and you cannot be a Brit who moved to Asia. You have to be of Asian ancestry. Chinese, Japanese, Vietnamese. If you're taking this drug, you got to get tested. So here's an example of how, even though we are having a debate and an argument about the utility of race, the FDA is plowing ahead, saying we recognize that genetic variation is racially specific and it impacts clinical outcomes, and therefore we're going to mandate that you, as a pharmaceutical organization, address this, and this is how they've addressed it. But we at UCSF, we actually don't believe it's all genetic. We believe that there are clearly social factors, environmental factors, that do interact with genetic factors. The interaction of these factors plays out in disease, and through the rest of my talk, I'll talk about how that happens. But for the beginning of my talk, I'll talk about genetic factors and how it plays out in contemporary populations. So, as a young resident, I was intrigued by this slide, and what was fascinating to me is that in the United States, the populations with the highest and lowest asthma prevalence are Puerto Ricans and Mexicans respectively. Despite that, even though that all the other populations, Asians, African Americans, and Caucasians fall in between, and the vast majority of research, about 90% of publicly funded NIH dollars focusing on Caucasians, the two tails of the extremes, high and low, were two Hispanic groups. Now, good epidemiologists will say, well, this is a reporting bias. Perhaps Puerto Ricans over-report asthma, Mexicans under-report. Now, I would have to agree with you on that, and that's something that we have to ask. But when you look at death rates from asthma, these are bona fide death rates in kids from asthma. You see that they mirror the same trends. Now, clearly, social factors play a role, environmental factors play a role, But when I was a young research fellow, I asked the question, could biologic factors play a role? And that's been my life's work ever since. So when I was not even finished my residency, I came up with the idea for a study called GALA, Genetics of Asthma in Latino Americans. And essentially now we have GALA 1 and GALA 2, and these are the populations that I'll talk about throughout my talk. In GALA 1, we recruited Mexican and Puerto Rican families from 4 geographic sites: San Francisco, Mexico City, New York, Puerto Rico. We also included ethnically matched control. We are currently doing GALA 2, which is called Genes, Environments, and Admixture in Latino Asthmatics, in which we're recruiting 4,000 Hispanic children with and without asthma from 8 clinical centers all throughout the United States. And in this situation, we're triangulating with social epidemiology, environmental epidemiology, and genetic epidemiology to see which factors are causative. So enough for those 2 populations. This is what we recruited. We recruited families, so mom, dad, and an asthmatic child, and this is going to come into play down the road. So in all of our children, whether they were in New York or Puerto Rico or San Francisco, we brought them in to perform what's called spirometry, where they breathe in and out of a machine, and what that allows us to do is get a quantifiable measure of how tight their airways are. Okay, and this is a classic flow volume loop, top being exhalation, bottom being inspiration. And what we do is we get a quantitative measure and a reproducible measure of lung function, and that's called FEV1. Then we give them a drug called albuterol, and then we repeat it before and after albuterol spirometry. And what that allows us to do is get a reproducible and quantifiable measure of drug response. So these are the key phenotypes that I'll talk about. So one of the coolest findings that we had was our first publication. And that's this slide here. And we were the first to demonstrate, at least for lung disease, but probably for other clinical outcomes, that the strongest predictor of drug response in our hands was ethnic background. And what this slide demonstrates is on the y-axis we have drug response. So the higher the better. On the x-axis we have children under the age of 16 on the left, greater than the age of 16 on the right. And no matter how we sliced or diced the data, the strongest predictor of drug response was ethnic background, regardless of geographic location, regardless of SES, regardless of concomitant medication use, regardless of severity. But the fact that you said you were Puerto Rican meant that you had about to have low drug response. We have gone on subsequently, and I won't talk about this more than this, that to replicate these results, and we've gone on to replicate that African American children also have differential response to drugs. And in fact, a paper appeared last week in the New England Journal of Medicine in which one of the strongest predictors in determining management of children with asthma, drug response management, was ethnic background. So they built upon work that we published from back in 2003. So this is cool because we start digging a little bit deeper. What does it mean to be Hispanic, or what does it mean to be Puerto Rican? Okay, so this is where our research starts taking off. So one of the obvious questions is, what do we use? Do we take for face value on FOSS what you think you are, or what you say you are, or do we bypass that and measure genetic ancestry? Okay? Now, when you start talking about Hispanic populations, this is a slide I borrowed from Rick Kittles. When you start talking about Hispanic populations, you got to dig a little deeper. And this is true not only for Hispanics, but all African American populations. These 2 populations are relatively young, less than 500 years old, 1492. And what happened is Europeans set sail from Spain and Europe, came to the New World. Subsequent to that came the importation of African slaves. The size of the arrow is representative of the proportion of the distribution of African slaves to the New World. So even though in the US we tend to think that we got a lot of slaves, the vast majority went to the Caribbean and went to South America, including Mexico. And in these populations they were subsumed, they were embraced and are now part of the general population. Okay, so what that really means is that contemporary Hispanic populations, and I hope you guys can see this, are really a compilation of three major groups: African, Native American, and European. And the resulting mestizo population, which you guys have in here in New Mexico, is a proportion of these ancestral populations. So this individual has 50-50 Native American, European, a little bit of African. This person has more African, more Native American. Okay, so this is a cartoon. So what do we do to actually get at how African you are, how European you are, how Native American you are? Well, what we did is we paired up with some anthropologists, Mark Schreiber in particular, and Mark goes around the world and samples populations, and pure populations, or quote-unquote pure populations. And what he did was he sampled, say, pure Africans from Africa, various Native American tribes, various European populations, and we genotyped them for genetic variants, what we call SNPs, single nucleotide polymorphisms. These are just those misspellings that I talked about earlier. And we looked for those misspellings that were more common in one population than another population. And what those misspellings give us is they not only tell us information that you have, a mutation, genetic mutation, in which a C was transmitted or replaced with the T, but markers that are more prevalent in one group versus another tell us information, a little bit of information, about an individual's racial background. Now, we call those ancestry informative markers, and I know you can't see it very well, but we call those SNPs, ancestry informative marker aims. Now, one or two markers won't give you much information, but kind of like a collage, if you're thinking about making a collage, the combination of hundreds of markers, thousands of markers, or 1 million markers can give us a pretty good estimate of who you are. And to put this in context, everybody here has probably seen CSI, right? There's a crime scene, there's blood on the wall, forensic pathologist comes in, wipes the blood off, they do genetic testing, and they give you a probabilistic score of the race of that individual where the blood came from. 70% likelihood is Asian, 30% likelihood it's European. It's the same method, it's the same toys. But we took these toys and wanted to ask the question, can we apply them to clinical disease? Are they relevant? Well, so we had Mexicans and Puerto Ricans, and we asked the question, what is a Mexican and Puerto Rican from a genetic point of view? And we took those ancestry informative markers and we came up with group averages, and this is what we found. We found that by and large, Mexicans had significant component of Native American ancestry shown in red, European shown in yellow, and African shown in green. Puerto Ricans, on the other hand, had much higher African ancestry, less Native American, much higher European ancestry. I hope no one's colorblind here, and I apologize if they are. Now, mind you, this is a group average. Okay, so we just took all of our Mexicans, all of our Puerto Ricans, and combined them. So these are the numbers we got. But when we looked at individuals, this is what we got. So here, each bar represents an individual. So individual number 1 is 100% Native American. Individual number 49 is 100% European. I'm like individual 61. That's why some people call me the undercover brother. Individual 92 is half African and half Native American. And here's where I really value doing your own field work, because I went out and actually recruited these subjects. I was there at the interview. And in order to get into our study, we had the parents there, and the parents had to self-identify themselves, their biologic grandparents, and their child as being either 100% pure Mexican or 100% pure Puerto Rican. Anyone that said otherwise was excluded from our study. So despite our best efforts to be epidemiologically correct, we got this fruit salad. And it's actually, this fruit salad is one of the reasons why geneticists had systemically excluded racially admixed populations up until a couple of years ago. They're too complex to study. And the reason being is that the genetic variation here can lead to false positives, it could lead to false negatives. No one knew how to deal with it. Well, lots of new methods have come out. The genetic science has advanced, statistical methods have advanced. So now we can really measure an individual's true ancestry and adjust for it in our statistical models. And now the question is, can we leverage that? Can we flip the coin? Can we leverage it to see whether or not we can learn new things about ancestry and its role in the risk of disease? So what if we took one individual? So individual number 60 on the top. And what if we just, remember we're looking at an average there. This individual's got a little bit of African, a lot of Native American, a little bit of European. Now what if we looked at their chromosome level? So for example, this is a cartoon of a Hispanic individual. Let me drop this slide. Just for a few minutes I want to drop this slide, these lights. This is what a cartoon of an Hispanic individual might look like. You might have on chromosome number 1, large chunks of Native American ancestry, large chunks of European, small chunks of African ancestry. Well, just suppose that a disease gene originated in one of these founding groups, just say European ancestry. Presumably, an individual like this that had more European ancestry would have a higher probability of inheriting that European risk gene. So that's how it all works. So let me give you an example of a real-life example. This is a karyotype, so chromosome pattern of an African American individual. And in the United States, we know that African Americans are about 20% African or European and about 80% African. That's on average. Well, Steve Hauser was interested in studying multiple sclerosis, which is a degenerative neurologic disorder. Multiple sclerosis only occurs in Northern Europe. Almost absent, if not completely absent, in Africa. But people like Montel Williams, who's African American, have multiple sclerosis. So Steve Hauser, who's the chair of neurology at UCSF, postulated that perhaps in African Americans with multiple sclerosis, each of them inherited a European risk, genetic risk factor. And so what he did is he got on the Montel Williams talk show and said, if you are African American and if you have MS, send your DNA to UCSF. And what they did now was they got all this nice cohort of African Americans with MS and they ran all those genetic markers. Because presumably, if it's truly European, you can a priori exclude the African component. And so what they did is they did that, and what they found was really cool. They found that on chromosome 1, everyone that had MS had a European marker that turned out to be ubiquitous amongst all the patients with MS. What they're now doing is they're now trying to do what's called fine mapping to identify where in that region the disease-causing allele is. This is called admixture mapping, and this came out just a couple of years ago. But here's an example of how we can leverage the genetic diversity that exists within all of us to scientific advantage. Now, clearly, this was a benefit for African Americans with MS, but who really benefited? Caucasian populations with MS. So now we're beginning to play one population off to the other, the diversity in one individual's genome compared to the diversity of another person's individual genome. So these are cartoons, but this is real data from a Puerto Rican in our own study. And this is real data from 1 million genetic markers, or what we call SNPs. And these are all chromosomes, chromosome 1 at the top, chromosome 22 at the bottom. Each of us inherits one copy from mom and dad. So each chromosome represents 2 chromosomes actually, so chromosome number 1. But what was really cool is because now that we had ancestry on these genetic markers, at every place along the chromosome, every place along the genome, we can assign ancestry. So for example, if I looked at chromosome number 1, the first part is European. You move to the right, second part is Native American. A little further, second part is African, and all the way down. So basically, admixed populations are a mosaic of ancestral populations. So Puerto Ricans, Mexicans are really 3 major groups: African, European, Native American. On a global level, we could say that, but on a chromosomal level, we could say that as well. So now the question is, can we leverage this? Can we use this to identify new risk factors, new targets in the genome to really hone in on? So what we did is we did a thing called admixture mapping.